Currently at my job, I'm coaching quite a few trainees, and one problem that is somewhat consistent across all of them is a lack of problem analysis and just basic knowledge of data structures. So I was thinking of just trying to solve a few problems, more or less live. I'm saying more or less live because I'll most likely read through the description first. It's not going to be that interesting to watch me just read silently for a few minutes. But I want to work through the problem in a more or less live setting without knowing the solution, just to demonstrate how I approach the problem. Right, so I can kind of summarize what the problem is. It's also on the screen. I'm going off LeetCode here. Basically, we are given an array, and it's supposed to represent a stack, like a stack of cards, for example, with the top of a stack being the beginning of the array. We can draw a card and keep it next to us somewhere, or we can put a card back. We can put any card back, but we can only draw the topmost card. So those are the operations we have. We are also given a integer, which denotes the total number of moves. I'm going to assume it's a positive integer. Well, it doesn't really matter because actually it's probably written down here. Yeah, k is... That's actually not written. Okay. No, it is, sorry. Yeah, it's between 0 and 10 to the power of 9. Yeah, sure, whatever. And we are supposed to return the maximum value we can... that'll be the topmost element after we do k moves. So basically, we're allowed to manipulate the stack. We have to manipulate the stack for exactly k moves, and then whatever values on top, we want that to be as large as possible. Then they give a few examples here on, like, if we have this array here and number 4, then we can remove, and add the 5 back, and then that would be 4 moves, and therefore the 5 would be on top. Of course, it is possible, and this also indicates that it is possible to get a stack number configuration that makes it impossible to have a top card. How that is possible, I'd like to think about in a second. But first, I just would like to play with a problem a bit, see how it behaves. Doesn't seem terribly difficult, but if we, for example, have just no moves, let's just say 0 moves, then whatever's on top is on top. We're done. We have no option here. I just cross a card out if that's the card on top. So if we have 1 move, we also have no choice. It's the second card. Because we have to draw once, that's the only option. We can't put a card back. We have 2 moves. Our options are to draw twice. To draw twice, that leaves us with the last one. Or to draw once and then put 1 back. So we can show card 1 and card 3. I can't draw it 3. If we look at 3 options, that means we have 4 cards. We can get to the last card again by drawing 3. We can draw 2 cards and put one of the 2 cards back. That means we can access both of them, and we can draw one card, put one card back, draw one card, but that's already in this data set. We can see we again can't access this card, and in fact it should never be accessible, because we have always, this means we have used up all our operations except one, and that means we're in this case. So we know we have to either draw or put a card back, which would be inserting. So we cannot ever access this card. But we can always go to the point right before. So everything before this section is always accessible. So with this insight, we can now reformulate, simplify the problem. We just want the maximum out of from 0 to k minus 1, which is this area, or k minus 2, sorry, or k, because we have 0 index, so minus 1 would be this one here. Those are the indexes that are valid. Now, there's a hint that we can get a invalid state. Well, what possible invalid state could we get? That is if our if we have to draw. That's the only time we can get an invalid stack, because the only time we can end with no card on top is when the stack's empty. That means the last move had to have been a draw. And that means we can only fail on odd numbers, because every time we put a card back, we have to draw once for that card. So a put back operation costs us always 2 moves. Yeah. And if we have more than one card available on the stack, so let's say the stack is size 2 or larger, then we can always just remove, draw, put back until we used up all of the things, and then we either drew the last one or we put the last one back. But either way, we're not going to end up with an empty stack. So the only option is for an invalid stack is stack size 1 and k is odd. So we can encode that fairly simply. We just look for num's length. If that is 1, and our k number is odd, taking mod 2 will just be 1 on all odd numbers, we can return -1. Now, there's another question to consider. We always looked at the maximum possible array. So what happens if the array is shorter? Let's say the array just goes to here. Well, now we can draw all of the cards, basically, and just end up with any card we want on top, because we have 2 moves left. At least 1 move left, so we can, if we drew all of them, we can put any card back. And it doesn't matter how many we have, because we can just waste moves until we are in that state. And we have this 1 free move we can always waste on drawing the last card and putting it back. So, yeah. That leaves us with a last case. So let's take from nums all elements from 0 to k-1. Slice is exclusive, so This is also elements 0 to k minus 2. And we want to also take the element at nums k. Because that's, if we drew k minus 1 times, the kth number is going to be on top. This gives us a array, and now we can just draw our max on it. And I'm just going to use an aggregate, a reduce, which has, let's say we have a maximum number, a number. If maximum is larger number, we accept maximum, otherwise we accept number, and we just start with -1, for example. This is going to be our maximum. We can just return this. And I think that is it. Now, slice will only take as many elements as there are. That means if we run to the end of the array, it'll just stop. Now, nums of k can be undefined because it could be out of bound. Since this is TypeScript or JavaScript, this will just default to undefined instead of an exception, so we don't need to do any boundary checking on whether we're still within the array or not. We can coerce this to a number. We know that there is at least a positive number larger than 0 in here, because every number in nums is larger than 0. And we know that nums is at least length 1. So it cannot be that no, it can be. There's one case where this can be. And that is if the array is length 2 and k is 2. No, k is 1. Right? Let's say we have a 2. Array length is 1. Then we take elements up to here, which is none. Wait, no. We take like this. So this should be on k is equal to 1. Then we take all elements before here, all of these. And if the array is only length 1, but that is that's not possible anyway because of this statement. But yeah, right. So this is not possible anyway. So I don't think this is a case we need to care about. So we can run this. Can't find nums. Yeah, can't type. Nums. Run code. Seems to work on the at least sample. Test. Output expected. Wrong answer. Input k is 0. Output 6. What does a slice of a negative number do? If we have an array, like 1, 2, and we say slice 0 minus 1, what happens here? I suspect it'll run to the end. Ish. It wasn't the end. But it was more than 0. It's all but the last one. So the negative index is from the back, I'm assuming. So if we run this code and expect just the first 2 elements. Yes, so we need to make sure k is positive or larger than 0, larger equals 0. 0 should be none, hopefully, and not all of them. That is none. Okay. So we can take a const, which would be the max, the end. Let's call it end, and that is k minus 1. Smaller 0, and then it's 0 or k minus 1, and then we can just put our end in here, and this should work now. It did. Right. So as far as performance of this is linear time. We are copying the array at worst case, once the length of the array, and then the reduce goes once more through it. So it's 2n, but that's runtime wise still n. Space complexity would be also n linear. We could do this with a with just a loop and track the indexes and skip the copying. That would be a bit more efficient and would use less space, but in linear time, I'm really not worried about any of it, and this is a lot simpler to write, so I'm going to leave it as that as well. Right. I'll leave it at that, and